All right, next up is talking a little bit about solving some equations, maybe at the beginning of an algebra class or as you're working into some pre-algebra and that type of thing. I gave an example here. We're going to work on just the basic idea of solving an algebra equation that might look something like 2x subtract 3 equals 5. The one thing that I'd really like you to be aware of is just a little bit here. I try to tell students when they're asked to solve, solve to me means isolate the variable. So you're going to manipulate an equation and you're going to try to get, in this case I use x as the variable, but you're going to try to get x by itself. If the variable is something else, you're going to get that letter by itself. So in this case right here, I'd love to take this equation and ultimately in the end, I would like to have that thing all by itself, which means I would love to have x equals. I'd like to get rid of that 3 and that 2 that are on the same side there. So that's my goal here, is to isolate the variable, getting x by itself. I'm going to really focus on using opposite operations or inverse operations. Whatever's being done, I'm going to try to undo that when I'm doing it. And what I do to one side, I'm going to do to both sides. I like students to think of, when you're solving an equation, even though 2x minus 3 looks a lot different than 5, if I focus on this as the left side of the equation and this is the right side, they certainly look different. The equation tells me, the equal sign tells me that they are the same. Even though they look different, they are the same. So going back to this, whatever I do to one side, I want to do to the other side, because I have two things that are the same, even though they look different. If I decide to subtract 100 from this side over here, I need to subtract 100 from this side over here so that I balance that out. I used to tell students that an equation was like a teeter-totter. However, I guess I realize now that a lot of the playgrounds maybe don't have teeter-totters, but in the old teeter-totter, if one person sat on this side, assuming the other person on the other side weighed the same amount and that we were the same distance from the center here, the teeter-totter would balance. If one side weighed a little bit more, it wouldn't balance. And I like students to think of a teeter-totter as an equation. Both sides are equal, even though the person on the left side may look different than the person or persons on the right side. Even though they're different, they're the same. If I add weight to this side, if I want it to balance, I have to add weight to that side. So that's going to be my focus on this. So let's move to the first problem, and we'll do the problem that I had in the example. We're going to solve 2x minus 3 equals 5. We're going to work hard to try to get x by itself. The first thing that I always like to do here, and I'll use a different color, is I like to get the term that includes x by itself. So I'd like to leave the 2x alone to start with, and I'd like to focus on the subtract 3. Remember I talked about opposite operations. So if I am subtracting 3, the opposite would be to add 3, and I am adding 3 to the left side of the equal sign. And I'm able to do that as long as I add 3 to the right side as well. So I'm going to balance this equation out by adding 3 over here and also adding 3 to that side. The minus 3 and a plus 3 are opposite numbers, and they're going to basically combine to be 0. They're going to knock each other out, leaving me with simply 2x. I was able to get these two numbers right here to cancel each other out, and then simply 5 plus 3 is 8. So I was able to get rid of the subtract 3 by adding 3 to both sides. Again, that's an opposite operation. In this case, I have 2 times x. I'm going to use the opposite of multiplication, which is division. So I will divide this side by 2, and it's certainly legal to do as long as I divide that side by 2 as well, remembering that this is an equation. The nice thing is here, the 2's will cancel, leaving me with simply x, which, if you remember, that was my goal, was to get x by itself. And 8 divided by 2 turns out to be 4. In other words, my missing number in this equation would be the number 4. If I were to plug 4 in here, 2 times 4 is 8, subtract 3 is 5, and that number does work out in terms of solving that equation. So using some opposite operations, doing the same thing to both sides, certainly seem to work out. Let's try one other quick little example here. In this case, we have x divided by 2 plus 4 equals 5. I'd like to solve this equation for x, and in this case I'm going to try to leave this by itself. So I'll leave the x divided by 2, but I will subtract 4. Notice I looked at the addition of 4 and I used the opposite. What I do to one side I also do to the other side. The plus 4 and the minus 4 would become 0. I would be adding 0, which I don't need to write, so they've kind of knocked each other out. And 5 subtract 4 is 1. Now I look at this and it says x divided by 2, so the opposite would be to multiply by 2, and what I do to one side, I simply do to the other side. Those are supposed to be little multiplication symbols there. In this case, the 2's would cancel, and I'm left with x equals, because the 2's drop out, x is the only thing left there, 1 times 2 would be 2. If I were to check my answer here, if I put 2 in for x, 2 divided by 2 is 1. 1 plus 4 turns out to be 5. So I was able to get this x. I was able to solve it, but I was able to get it by itself by using the opposite of adding 4, subtracting 4 from both sides, and the opposite of dividing by 2. I multiplied this side by 2, and I also multiplied that side by 2, and I was able to get a final answer of 2. Hopefully this little equation helps, or this little video helps you out solving some basic algebra equations.